Hi guys, now I'm going to talk about the surface area of a surface of revolution, okay, or a solid revolution. So you have a function of, you have y as a function of x in here, which makes this curve, and this thing is going to go around the x-axis, okay, so this is going to go like this, it'll go around the x-axis. And it'll make a solid revolution. Now, in the solid revolution, you know that's going to be like a solid, okay, something like this. Let me just get a three-dimensional picture in here. Something like that, all right? So this is a solid. Now, we're not going to calculate the volume of the solid anymore. If we were going to calculate the volume of this solid, okay, it'll be, if we're calculating the volume of the solid, it will be using the disk method, pi, right, times f squared of x, f squared of x dx. Okay, so yeah, and the x was going to go from something to something else, because it will be the disk method, okay? The first disk, like this one in here, like this beige stuff, plus another disk, plus another disk, plus another disk. So this was going to be the volume using the disk method. Volume using disk method. Okay. What about the volume using the shell method? It was going to be 2 pi, all right, times, then if it's around the x-axis, we're actually going to calculate, we're going to have horizontal bars, okay, and we're going to calculate dy. So it was going to be 2 pi times y. This y right here is actually going to be the distance from the horizontal bar to the x-axis, right? So it was going to be that, and you could say f of y, which was going to be the length of that stuff, of that bar, okay, and it was going to be dy. So this is this stuff, volume using the shell method, okay? Now, if we're going to calculate just the surface area of the solid revolution, so it's the surface area of the solid revolution, then we just care about the surface. We don't care about the inside space, all right? So what is it going to be? Well, if it's just the surface area of the solid of revolution, okay? I'm going to put it like here. So it's going to be 2 pi, if the solid revolution is around the x-axis, okay? It'll be 2 pi times the integral of f of x times the square root of 1 plus the first derivative, well, I'm going to put it over here, squared dy dx, okay? So it's going to be 2 pi times f of x times the square root of 1 plus dy dx squared with respect to x, okay? And if it's a function, if it's x as a function of y, then it's just going to be the same, the analogy, the same thing. It'll be 2 pi times f of y times the square root of 1 plus dx dy squared dy, if the surface of revolution is around the y-axis, okay? I don't know, some books call it a surface of revolution, others call it a solid of revolution. It is a solid, but let's just say that you just care about the surface. But why? Well, So let's go over here again. This is going to go around, okay? So at this point of x in here, this is going to be the radius. Now at this point of x, what is going to be this radius? It's going to be f of x, okay? I mean, you have f of x everywhere, but let's just think about this one for this x and 0 here. So if this point right here goes around the x-axis, is going to make a circle. Okay, so what is the circle going to be? Well, the circumference of that circle, which contributes to the surface of revolution, or which contributes to the surface area of the solid revolution, is going to be 2 pi times r. And what is r in this case? It's going to be f of x 0. Okay, but there's something else that you're forgetting too. How much does it go? And you go like, what? Okay, how much does it go to the horizontal or up or down? In this case, in the case that we're stepping up to the right one step at a time. Okay, so remember that when you have something like this, right, and you get a zoom like over here, okay, a very small zoom. I'm gonna make something very small like here, like a square, okay, and you zoom that out like this. You have this little area and you zoom it out. Well, it's going to go from here all the way down there, but it's gonna really, hold on. Let me see if I can use another tool in here to do this stuff. Okay, kind of like here. It'll be almost like a straight line. It's going to approach a straight line. And as you zoom in to this stuff in here more and more and more, this is going to approach more and more and more a straight line. Okay, I wasn't supposed to do that, but you get the picture. Don't worry about this thing here, okay? This doesn't exist. It's just going almost like a straight line because you're zooming in. Well, so for this square in here, you're going to have 2 pi times the f of x0, and then you go like, oh, hold on a minute, hold on. It's not going to be f of x0 because in here you have an x, in here you have another x, in here you have another x, so x0 is going to be which one of these? Well, as these things, because this is a very zoomed in area, okay, around here. So let's just say that you zoom infinitely in. The distance from this point x0 to x1, so x1 minus x0 is going to approach 0. Okay, so you can say that the f of x0, let's just say instead of f of x0, we can say f of c. C is going to be one point in here, and it doesn't really matter. Why doesn't it really matter? Because as you zoom in more and more and more, x1 is going to get even closer to x0. Okay, it's exaggerated here in the screen like this size, but this is just for you to see. You got to see that you're zooming in infinitely. Okay, so it doesn't really matter. So what is going to be the radius at this point C in here? Okay, let's just say that the x-axis is in here and the y-axis is in here. So this point, the radius is going to be this distance right here. Okay, this is going to be the radius at this point for the f of x0, or for the f of c. Let's just say that x in here is c. Okay, so you're going to have 2 pi f of c, which is going to be the 2 pi r, making a circumference, but that circumference is going to extend to the right a little. Okay, how much is it going to extend to the right? Well, it's going to extend this length. Pretend that this is approaching this thing here, is approaching a straight line infinitely. Okay, it's approaching more and more straight lines, so you can consider this a straight line. Well, how much is it going over here? It's that same stuff. You have you got a horizontal spacing here, and you got a vertical spacing here, okay? So, what is going to be the horizontal space? Well, for convenience, we just consider it 1, remember? And how much is it going to go up? Well, I don't know how much it's going to go up, but I know that for this thing that approaches infinitely a straight line, what is going to be the slope? The slope is the rise over the run, right? So the slope is the first derivative. So if I find the first derivative, I find the rise over the run. And the rise is this thing here, which I'm going to call d, this distance. The run is just 1, so it's going to be d divided by 1, which is d. But hey, d divided by 1 for this thing that approaches a straight line is what? It's the first derivative of the function at the point C, at this point right here, okay? So knowing this, so d divided by 1 is equal to this, all right? So I have d divided by 1 equals d, and d divided by 1 also equals to this. So this equals the first derivative at the point C, all right? So what is this length right here right now? Well, it's going to be the square root of the first side, okay? Because this is a right triangle, okay? You see the 90 degree over here? So it's going to be the first side squared, which 1 squared is just 1, plus this d squared. But what is d? Well, d equals the first derivative at the point C. So it's going to be like f squared, the first derivative at the point C, okay, squared. But hey, we're not just worried about the point C. As you do the same thing, okay, so it's going to be 2 pi times this stuff, which is the r right here, this distance, okay, which is going to give you a circumference, just going to give you a circle, and we're going to extend that circle this much, and this much is what? Is the square root of 1 plus the derivative of f at the point C squared, okay? But forget about this x1 in here, all right? Hold on. Okay, but this is just for the point C, and we want to calculate the whole surface area from here to here, for example, okay? So we have to integrate this. It'll be the integral of 2 pi f of x, the square root of 1 plus. Since we're doing y as a function of x, we can just do y prime, okay, squared dx. And if we're doing x as a function of y, then we use this function here. And that's it, guys. Now I'm going to show you an example, right? Most of the times I explain the theory in one video and I do an example in the other video, but this time I'm just going to do the example over here. Just erase all this mess. Okay. So let me get an example here from the book. Find the area of the surface formed by revolving the graph f of x equals x cubed. So it wants to know the surface area of this, okay, not the volume, just the surface area. Well, let's do that. It'll be the integral, and x is from 0 to 1, so it'll be 2 pi times the integral from 0 to 1 of f of x. What is f of x? X cubed, okay? Now, you have to do times the square root of 1 plus, let's find the derivative. The derivative is going to be 3x squared, okay? So the derivative squared is going to be 9x to the 4th. So it'll be 1 plus 9x to the 4th. All right. Let me just think about one thing in here. All right, it'll be the integral of this with respect to x, okay? Yeah. All right, so how do we do this? Well, this is going to be the inside function, and what is the derivative of the inside function? It's 32x cubed. You got an x cubed in here, so perfect. We can just integrate directly, okay? The integral of this is going to be 2 pi times, you have 1 plus 9x to the 4th to the half, right? So we're going to go 1 plus 9x to the fourth to the 3 halves divided by 3 halves. So we're going to multiply, I'm going to put a 2 in here and a 3, because divided by 3 halves is multiplied by 2/3, right? And what else? Divided by the derivative of the inside function with respect to x, which is 36x cubed. So I'm just going to put a 36 in here. What about the x cubed? Am I going to put it in here? No, because you have this x cubed, okay? So if I copy it here, you're going to have to simplify these two anyway. So who cares? Don't put it, right? It's just going to be over 36. And that's it, guys. Now you have 2 times 2 in here, which is 4. Okay, 36 divided by 4 is 9. So I simplify this stuff with this stuff. I'm going to put a 9 in here. All right, 9 times 3 is 27. So let's put a 27 here. And now this is the integral, and we have to integrate this whole thing with from 0 to 1. All right. Okay, so let's do that. Okay, so it'll be pi times 1 plus, if it's a 1, 1 to the fourth 1 times 9, right? And this is being elevated to the 3 halves divided by 27 minus pi, and then you have 1, we're going to plug in a 0 here, so the second term just becomes a 0, okay, to the 3 halves divided by 27. So we're going to have like, this is going to be pi, because there's pi everywhere over 27, I'm going to factor this out. All right, and this is gonna be, what is 10 to the 3 halves? Okay, 10 to the 3 halves, guys. You already should know this. It's 10 cubed in a square root. Okay, so if you have 10 cubed, you actually have 10 squared times 10, because the power of this 10 equals the index of the root. You can just take this 10 out. So it's going to be 10 square root of 10. This is this first term, okay? And then you have minus 1, right? Minus 1. Because 1 to the 3 halves is just going to be 1 times pi is pi. So since you got the, so this term in here becomes pi over 27, but because we factored it out here, you got a minus 1 there. So it's 10 square root of 10 minus 1 times pi divided by 27, and yeah, that's right. And this is approximately, this thing here is approximately, I'm going to put it here, okay? It'll be 3.563. 3.563. So what is this? What does this mean? Well, it means that it's this area right here, okay? It's everything that's coming outside. It's this thing here, plus this stuff in here, all going around like this, and going in here, all this outside area, going on the other side, coming on the other side in here, but not the inside part. Okay, you can see that this lighter beige in here, or lighter yellow, becomes the inside part. No, not that, because you don't want the volume. And you just want the area outside. Because, for example, let's just say they have a piece of paper in here. You got an area over here, and you have an area on the other side. Well, this is just the area on one side, okay, on the outside of the thing. And that's it, guys.